These exercises on curly arrows are mainly to help with the course on conjugation in organic chemistry, but they apply equally to any mechanism in which bonds break and bonds form. But remember, in conjugation, no bonds break and no bonds form. All you're doing is moving pi electrons. The first main point to get is that curly arrows are like electrons in a circuit. They will flow in one direction. They won't sort of head towards one point or away from one point. Whenever you draw a curly arrow, the tail of the arrow is always where the electrons start, and the point of the arrow where the barbs are where the electrons finish. So that if you have a positive charge, like an H+, electrons will never be heading from that, because that's not a pair of electrons, they are just a proton. Electrons will always head towards the H+. So curly arrows are pairs of electrons. Electrons are negative, they're attracted towards positive charge. So curly arrows should be always heading towards a positive charge. If you have them drawn heading away from a positive charge, that will be wrong. If you have a negative charge, which will be part of a lone pair, electrons will head away from the negative charge. If they're heading towards a negative charge, again, that will be wrong. So once again, if we are a beginner with curly arrows and resonance structures, it's a good idea to draw in all the bonds to make sure that we don't make any mistakes. So here we have an allylic carbocation. On the left hand side, just drawn as a skeletal formula, and on the right hand side I've put in all the bonds to hydrogen. So first of all, how do we know there are 3 bonds on the carbocation? Well, for that we need to think about formal charge. Formal charge is a very useful concept which allows us to basically keep account of electrons and protons. So for that carbon, it's in group 4, a valency of 4, so we put a +4 charge. So we're saying that there are four protons available to be balanced by the electrons in that valence shell. So for carbon, group 4, we put +4. Then for each bond, if we put 3 bonds, 1 electron for each bond, that's -3, a net charge of +1. In other words, to get a net charge of +1, we have to draw 3 bonds. So now, when we see a plus charge on a carbon, we can immediately assume there must be 3 bonds, without having to draw them. And on this slide, we've got an allylic carbanion. Again, on the left hand side, it's drawn with simply a negative charge on the end. And on the right hand side, we've put in 3 bonds. So why are there 3 bonds? Well, again, we start with the fact that carbon is in group 4. We put +4 for its valency. If we put in 3 bonds, that gives us -3. And in order to have a -1 charge, we must add a further 2 electrons, which is the lone pair, to give us a net charge of -1. So that means if you see a skeletal diagram with a minus charge on a carbon, once again you know there must be 3 bonds with a lone pair and a negative charge. So that means we can assume there is a lone pair, and we can use the negative charge to draw our curly arrows with. In theory we should really draw a lone pair, but it's quite acceptable to use the negative charge on its own. For an allylic radical, we follow the same procedure. Draw in all the bonds. Why is there 3 bonds? Well, again, carbon is in group 4, that gives us +4. There are 3 bonds, that gives -3. And an unpaired electron, that's -1, so the net charge is 0. So to summarise the previous few slides, we can really look at skeletal pictures and see that if you have a negative charge, it really is 3 bonds with a negative charge and a lone pair, but we don't have to draw that lone pair. If it's a positive charge, again there are 3 bonds with a positive charge. If it's a radical, there are 3 bonds with an unpaired electron. Notice that the curly arrow ended in a bond, not on the end carbon. So when you're moving curly arrows towards a positive charge, the last arrow will end in the bond before the positive charge, not on the positive charge, in a resonance structure. So for any conjugated system that has a carbanion as part of it, you start your curly arrows with the carbanion, which is really a lone pair, and move it away from there into the adjacent bond, and keep moving electrons in the same direction and finish on an atom. So that means you've created an anion where the arrow finishes. The only time you don't finish on an atom is if there's a positive charge that you're heading towards, in which case it will go into the bond just as before. This system again is a conjugated system which has a carbanion in it, i.e. it's got a lone pair, so that negative charge has a lone pair applied. But this is just to emphasise which parts of the molecule are conjugated and which are not. So if you look at the CH2 to the left of the negative charge, that's got 2 hydrogens on it. If you push electrons that way, again you'll be forming 5 bonds. So that cannot happen. There is no conjugation in that direction. We can push electrons to the right and keep going until the last double bond, and then we put the electrons onto the atom. That gives us the structure at the bottom. And I've circled the area which is now conjugated. However, if I carried on pushing curly arrows into the bond after the last double bond, again we would have a case we've now created 5 bonds around that CH2 carbon. That goes above its valency, therefore you cannot do that. So here we've got a case where we've got an anion at one end and a positive charge at the other end. So again, we start with the anion, push electrons into the adjacent bond, keep pushing the electrons in alternate bonds. At this time we finish in the bond and create that double bond in structure 2. Notice that the net charge is always the same in each structure. If you have a net charge of 0 in the first structure, every resonance structure after that must also have a net charge. So this is a good thing to check to make sure you're not making any mistakes. Notice also that the second structure will be much more important resonance structure compared with the first. So the overall electronic structure will look a mixture of both 1 and 2, but will have more of the second structure in it than the first. So just to confirm what we had in the last slide, here we've got a ring structure with an anion at the bottom and a double bond at the top. And if we put in all the CHs, we can now see we've got a CH2 in the carbon between the anion and the double bond. And if we push the electrons into the adjacent bond, we've now created 5 bonds. So we cannot do that, we've broken the valency of carbon. So there's no conjugation between the anion and the double bond. They're separated by an insulating CH2. When we're working with radicals, i.e. unpaired electrons, in this case we're going to use curly arrows with 1 barb on them. And this is the only case where arrows go towards each other, because one electron goes from one side to produce one electron for the bond, and an electron from the other one comes the other way to form the other electron in a bond. Remember, we need 2 electrons to form a bond. So start with the unpaired electron, move it into the adjacent bond, go to the next double bond and split the electrons so one goes to the left and one goes to the right, and keep going, and again finish on an atom. So the last structure will have the unpaired electron at the far end of the conjugated system. In the previous examples, we've shown the conjugation over the full extent of the conjugated pi system. In this one, we're going to show that by showing how many resonance structures you can create. And each time we generate a new one, we're going to basically move the minimum number of curly arrows to generate the next structure. So from 1 to 2, we've just moved 2 curly arrows, initially moving the lone pair into the adjacent bond, and then the next pair of pi electrons to finish on an atom. And we do the same pairs of curly arrows to generate 1, 2, 3 new resonance structures. And the more resonance structures we draw, the more conjugated the system is, i.e. the more stable it is. So in this final slide of these exercises, we're just going to consider the quality of resonance structures. It's not just the case of obeying the curly arrow rules and also making sure that the valency is correct, but does the structure make chemical sense? Is it stable? So in this first example, the electrons in a conjugated system with a carbonyl on the end are heading away from the oxygen towards the carbon. Now we know that oxygen is more electronegative than carbon, therefore you would expect electrons to flow towards the more electronegative atom, oxygen. So the second set of curly arrows are much more realistic as to what will happen. The electrons will flow from the left hand side towards the right hand side to give us a resonance structure with a negative charge on the oxygen.